Folks, so thank you for watching this video. What we have here is kind of the last part of, I don't want to say chapter 2 in general, but this is kind of the last like bulk item that we're going to be kind of looking at. So you obviously have been introduced now to quadratics, and again, you've obviously talked about the three forms. We talked about factored, standard, and then obviously the vertex form as well, or graphing form. Now, we also talked about, again, with vertex form, we talked about the stretch factor with the A value, the horizontal shift with the H value, and then the K value, which moves it up and down. So now what we're going to do is we're going to apply this now to every function. And what I mean by every function, if you had a chance to kind of take a look in your packet here, you're going to notice x cubed, square root of x, absolute value, 1 over x, the hyperbola, and then y equals 2x, the exponential. So all of these functions, in this case, are now going to be kind of using that a, h, and k values. So with that in mind, what we're going to do is we're going to just pretty much kind of hop right in here. I'm not going to do all of them because, again, we're going to have a couple of days to do this. So we're going to probably do maybe 3 or 4, depending on, again, how long this video goes. And then we'll complete them the next time, obviously, I see you guys, and then I'll let you kind of ask any questions that you have. So what you're going to notice, again, is a general trend. As we kind of go along, it's going to be pretty straightforward, but in this case, again, just keep that in mind. All right, so the first one we're going to start with is y equals x cubed. So we're just going to start with what the parent function looks like, and we're going to show you kind of how to graph it as well. So with that in mind, obviously, you have the y equals function here. And with that, what we're going to do is we're going to go ahead and hit the y equals button there. And then I'm going to go ahead and plug in x cubed so you can kind of see what it looks like. Okay, so again, you can use the caret key and then find it. So you're going to go ahead and hit the graph button there. And what you're going to notice then, obviously, is we kind of have this shift. So again, it kind of looks almost like a parabola, but in this case, what you're going to notice is this end ends up, but now this tail ends down. So again, that's kind of the point, and the reason why is because, again, obviously with that cube function, now it's going to be, obviously, we don't have the all positive results. In this case, again, we're going to have 2 values. So that's going to end down. So we're going to go ahead and make just a quick sketch of what this looks like. You can go ahead and take a look at the values here, specifically in the table. Now, what I'm going to show you is actually how to graph them eventually, and again, they're actually pretty straightforward. But in this case, when you're graphing them, just know that, again, the turning point, that one in the middle, is always going to be 0, 0. So I'm just going to go ahead and draw that in here with my axis. And then in this case, again, it does not need to be perfect, folks. Again, you can see, again, this is a very crude drawing. But again, you're going to get that idea once we graph those points. And I'll go ahead and grab another marker, or excuse me, another pen, so you can kind of see the difference there. All right, so the first point, again, we have a 0, 0, so I'm going to go ahead and put that kind of in the middle there. And again, I'm just going to kind of read the points. The ones that I'm going to kind of look at specifically are just going to be the ones that kind of can fit on my graph. You can go off to -3 if you want, so I'm just going to put -3 and -27. And then I'm going to do the values of -2, -8. And then I'm going to do the value of -1, -1. And then 0, 0. And then obviously what you're going to notice is these patterns continue. Now the nice thing is, again, much like a parabola, these, when we graph them, are going to have that same form. So we have that turning point at 0, 0. And again, if we're talking parent function here, in this case, the parent function, again, is going to be over 1 and up 1, actually. And then we're going to go from that turning point at 0, 0, we're going to go over 2 and then up 8. 3, 4, 5, 6, 8. So therefore, we're up there. Next one, we're going to now, obviously, as you can see, 327 is going to be off the graph. But with that in mind, I'm going to go ahead and reverse it. So from that turning point, over 1 to the left and down 1. As you can see, again, from the points here. Then we're going to go over 2 and then down 8. So 1, 2, 3, 4, 5, 6, 7, 8. And you're going to end up there. All right, so then you got that cubic function that looks something like that. So again, very much similar to a quadratic. The only difference is, again, obviously, one of the points kind of ends down, and then the other is going to end up. So we're going to go ahead and answer some information about it, just in terms of domain, range, some important points, yada, 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 with that. So the first one, the domain. The domain in this case for this one is going to be all real numbers. And the reason why is because, again, if you look, obviously the arrows are going down. Obviously they're going down at a pretty fast rate, but it's going to keep moving. So all those values from negative infinity to positive infinity are going to be included. The range, same kind of idea. Again, we start from bottom to top. In this case, again, all the y values are being used, so you can put all real numbers for that one as well. X and y intercepts, they're actually going to be both the same here as well, because with those values, they're going to be both at 0, 0. All right, and as you can see, any other important points? What I was talking about earlier, what we call the turning point, it's kind of like the vertex, if you will, for a parabola. It's the one that, again, kind of all the other points are based off of. So that one's, again, at 0, 0, much like the vertex as well. So therefore, we can just say turning point at 0, 0. Asymptotes, there are none for this one, because in this case, again, obviously it gets really close to a line, but excuse me, an asymptote is an imaginary line the graph will get really close to, but never actually touch. In this case, again, there's nothing that looks like that here. All right, so now the bottom part. This is probably, again, one of the more important things that we look at, because in this case, again, you're going to see how the transformations kind of line up the same way that we did with a quadratic. So in this case, we have an equation of a graph that shifts the parent function left to right. So what you're going to do is you're going to go ahead and write y is equal to, and again, I'm going to write the function that shifts it left to right, which in this case, what you're going to notice is, if I write it as x minus 2 quantity cubed, this is going to be what we have here for a cubic function. Now, minus 2, if you recall again, shifts the graph left to right, shifts the graph right to for a quadratic. And the funny thing is, it also does it as well for a cubic function. So therefore, our turning point is going to go, instead of at 0, 0, is now going to be at 2, 0. So therefore, now we have a cubic function that looks something like that. Now we're going to go ahead and talk about, okay, an equation of a graph that stretches vertically or compresses. Well, if we're looking at, again, stretch or compression factors, a stretch is going to take that entire thing and pull it apart so it goes up at a quicker rate. So if I write it, I'm going to write y equals 2x cubed. And if you think about it, the turning point is not going to change, but the values that are outside of 0, so these ones at negative 1, 1 or 1, 1, are going to be taken and pulled apart. So therefore, I'm going to try to kind of keep it closer to that y-axis, because in this case it's going up at a quicker rate. So therefore we have, again, our turning point there at 0, but in this case everything goes up, much like the stretch factor for a quadratic. All right, and then at the bottom here, you got the values. What it says here, the equation of a graph that shifts the parent function up or down. So this one, in this case, we're going to go ahead and write it as y equals x cubed, and then I'm just going to do plus 2. Now again, same thing as the h and k. The k value for our quadratic shifts it up and down, and the k value here is also going to shift it up with that cubic function as well. So therefore, we have something that looks like that. All right, and last but not least, the equation of a graph that flips the parent function upside down. Well, you can probably guess, again, same as a quadratic, we're going to have that negative a value or negative value out in front. And so therefore, we're still going to have that turning point at 0, 0, but instead, it's now going to look inverted. So in this case, the tail ends, okay, so the tail ends up now, and then now it's going to end down here. All right, so this is the parent function, so cubic, as you can see, in terms of 3. Now, what does the general form look like for this? Well, in this case, it's going to look very much, again, similar to what we had as a quadratic. The only difference is instead of having that squared feature, we're now going to have a cube function. So therefore, you have y equals a, and then x minus h quantity cubed plus k. All right, so hopefully, again, you figured out those values. Again, we're going to talk more about graphing them, so then that way, again, you won't even actually need a calculator for this. Again, just know that, again, the turning point, much like the vertex, and then, again, it's going to have this pattern here when we do. All right, so go ahead and flip onto the backside, and now we're going to talk about a square root function. All right, so square root functions look something like this. Y equals the square root of x. So I'm going to go ahead and plug it in my graphing calculator, see what it looks like. So I'm going to go second clear out, and y equals, plug in the parent function, second, and then the square button, and then value of x underneath. And then I'm just going to include those values there. So in this case, it kind of looks like a line. It almost kind of like looks like half of a parabola if you took it and kind of rotated it 90 degrees. And again, we don't obviously include the negative values because obviously it wouldn't be a function then. So what we're going to do is we're going to go to our table. And what you're going to notice is a couple of error points, and I'll explain why that is here in a second. But we're going to start with some of the values. -1 you can put there if you want. Again, you can just put error message or NA, because in this case, again, you can't get an output. And then the rest of them, we're just going to kind of line them up. So the first one, 0, 0. Next one, 1, 1. Next one, now it says 2 and then 1.41. What I'm going to tell you is don't use this point. Again, these points with decimals aren't as important. We want the integers, meaning again the values that are the counting numbers and their opposites. So 4 and 2 is going to be the next one that I use. If I keep shifting down here, 9 and 3. And then we'll just do one more just for the point of it. And then 16 and 4 there at the bottom. Now what you're going to notice is these points look very familiar because if you look, they actually are just the values of the quadratic actually flipped around. So instead of having, again, the over 1 up 1, obviously we have those, over 2 up 4, but now it's over 4 and up 2. So therefore, again, we actually have, again, a quadratic that looks very similar, obviously in this case, but with a square root function. All right, so I'm going to go ahead and draw my lines in here. And then I'm going to go ahead and draw the other axis. And now what we're going to do is we're going to include what the square root function looks like. So square root function, obviously it starts at 0, 0. So I'm going to go ahead and put that dot there. Next one, I'm going to go put 1, 1. So in this case, over 1 up 1. And then next one, over 4 up 2. 2, 3, 4, up 2. And then the other one, over 9 up 3. So I'm just going to put that on here. 3, 6, 9. Oh, 6, 7, 8, 9. And then up 3. So 1, 2, 3. And as you can see, now it's going up at a much slower rate. But again, if you kind of turn it sideways almost, it looks like, again, half of that parabola. So again, if it was rotated. So what we're going to look at now is we're going to say, all right, domain. So the domain in this case, if we're looking, obviously we start at 0 and we're going to the right. So therefore we're going to go to infinity. Remember the brackets and parentheses, just be careful with those. Range, same kind of deal. We start at 0 and it kind of keeps going up. In this case, again, it looks like it levels off, but it's still going to go to infinity there. Next one we're going to take a look at is what we call the x and y intercepts. Same kind of deal as with that cubic function and a quadratic. Both of them are going to have those values starting at the y-intercept. Now, other important points. Much like we talked about with the vertex with the quadratic and then the turning point for a cubic, this one for a square root actually has a starting point. And again, the starting point in reference is basically the last point that you can plug in into that square root function. Because if I plug in that value of -1, if you remember, value for that square root of -1, we don't get an output. Again, we plug in our calculator, it says error message. And the reason why is because, again, no two values can multiply that are the same to -1. So like 1 times 1 gives me 1, but -1 times -1 gives me +1 still. So with that in mind, again, just keep that for reference. Asymptotes, there are no asymptotes for this one here. And the reason why is because, again, there's no imaginary line that the graph will get really close to. So just keep that in mind. All right, and the next one, it says the equation of a graph that shifts the parent function. Well, in this case, again, we're going to shift that parent function left and right. So y is going to equal the square root, and now I'm just going to do x, and now -2. So instead of having those parentheses with a value on the outside, so a 2 or a 3 with the exponent, in this case now it's just going to be the square root of x minus 2. So therefore, I'm going to go ahead and do the same idea. I'm just going to shift that starting point over 2, and then it's just going to go on like that. All right, same kind of idea, equation that stretches or compresses the graph vertically. Same kind of idea when I multiply with the values for quadratic and cubic. I'm going to just take that value and multiply, so 2 times the square root of 2. So instead of now going up at a slower rate, it's going to go up at a quicker rate. Okay, so then it kind of levels off a little bit higher. All right, then we're going to go ahead and take a look here at the bottom. It says the equation of the graph that shifts the parent function up or down. We're going to do y is equal to the square root of x, but now in this case, that k value is going to be on the outside. So I'm going to have plus 2. I'm going to go ahead and put my starting point again up there. So the graph kind of looks like that. And then what we're going to do is says the equation of a graph that flips the parent function upside down. In this case, again, if I'm flipping this, it's going to be reflected. So it's going to be at 0, 0. And it's just going to kind of tail off. So therefore, again, kind of looks like the right side of that parabola now. So the last part, excuse me, we're going to go ahead and write the general form for the equation. Again, same as that quadratic and cubic function. The only difference now is we have a square root. So we're going to have a and then parentheses x minus h. So again, note that that h value, again, is still negative, even though we have a square root or a cubic function. And then we have the k value on the outside. All right, so in this case, that's our second one. Hopefully, again, you're kind of able to figure those out. All right, so we got cubic done. We got the square root function. I believe the next one is the absolute value. Sorry, my paper was messed up. And I think this is the one that we're going to finish up on here, because in this case, again, I don't want this video to go too long, especially with you guys all having stuff coming up. And I think we do not have a quiz today, but just keep that in mind with that. But again, we'll fill out these the rest of the week as we go along. So last one we have is what we call the absolute value. So the absolute value is kind of unique because in this case, it's actually much like a quadratic. If you ever plug in the absolute value into your graphing calculator, which again, we've done for some of you, it's going to actually create a distinctive letter. What we're going to do is we're going to go ahead and y equals, clear out that square root function, and then I'm going to go ahead and hit math. Number, so I'm going to arrow over, and then ABS is that absolute value. So then therefore you get that. So some of you again are going to have absolute value like spelled out, so just keep that in mind. Again, some of you don't have the bars because you don't have the newest and greatest calculator. So with that, you got the X value, and you're just going to keep that on the inside there. We're going to go ahead and hit graph. And you're going to notice now it kind of looks not like a U or not like kind of like an S, but now it looks kind of like a V. So again, that absolute value function, whenever we plug in a value into the absolute, again, it's the distance from 0. So keep that in mind. With the distance from 0, it's always going to be positive. And I always like to think, again, if you travel anywhere, you are always traveling a positive distance. And when you come back, you're not traveling that negative distance. You're still traveling. So those values are always positive. We're going to go ahead and flip to that table. All right, and we're going to go ahead and get some points. I'm just going to keep the values kind of simple here. I'm just going to do like -3. So if I plug in the absolute value -3, the distance from that is going to be +3. -2, I plug in the distance, that value from 0 is still going to be 2. -1, that's going to be 1. 0, obviously it's the same value, so again, it's going to stay there. And then if we plug in the positive values of 1, 2, or 3, obviously you're going to end up getting that distance that's the same there. All right, so we're going to go ahead and sketch that graph. So in this case, this XS one more time. Now what you're going to notice is then, obviously all those values are going to be positive. So I'm going to go ahead and start. What I always like to do is, again, I like to start right at the value point there. This actually, again, is what we call the vertex with an absolute value, so much like a quadratic. Now, in this case, we're just going to kind of follow the pattern. We go over 1, up 1. Goes over 2 from that vertex and up 2. Now, what you're going to notice is the pattern, again, is kind of like a linear line. It's going to go up 1 and over 1 each time. So, again, all the way to the top, and we can graph that function there with that. And then the same thing going to the left, so therefore we go over 1 and up 1, over 2, up 2, and then again that absolute value function just keeps going up at that consistent rate. Alright, and last but not least, we're going to go ahead and talk about some of the values here. Connect my line. What we're going to talk about is the domain range with those values. So domain, again, obviously if we look here, all the values are being used to the left, all the values are being used to the right, so therefore we got the domain as being all real numbers. Range here, again, same kind of idea as the quadratic. We start at 0 and then it goes to infinity, so no negative values coming out of this absolute value. Y-intercept and x-intercept, same again as always. It's going to be at the value of 0 and 0 for both of them because they're centered there. Now, other important points, this is what we call, again, the vertex, and the vertex, again, is just applying to the lowest point of that absolute value. So therefore, again, we have that there. Asymptotes, there's nothing here with those, so you can just again cross it out or write NA. And then we're just going to talk about the last part here at the bottom. So equations of parent functions, again, left or right. So again, if I'm thinking about moving it left or right, I'm going to do y is equal to parentheses x minus 2. And again, since again it's minus 2, it's going to be a shift to the right. So over 2. And then we have a v that looks something like that. The next one, if we're looking here, again, stretches or compresses the graph vertically. So what we're looking at then, so we're looking at that value being on the outside. So we're going to write y is equal to 2, and then point this, or the absolute value bars, and then x. Again, make sure that that 2 is not on the inside. That's actually what we call a horizontal stretch. And again, we're going to talk about that in pre-calc. So again, if you stick around with this, again, you're going to do that horizontal compression and stretch factor as well. That 2 value is just going to make that absolute value go up at a more consistent, quick rate. As you can see, again, on the original, obviously it goes up at a little bit quicker rate. It's being multiplied by 2. All right, and then the bottom here, it says the graph that shifts the parent function up and down. So we're going to go ahead and write y is equal to the absolute value of x. And then in this case, we're just going to add 2. So I'm going to put that there, and it's going to go up at that same consistent rate. And then the key value is limited on the outside. All right, and the last one, that absolute value needs to be negative when we reflect it. So we're going to do negative, and then the absolute value of x, because in this case, again, obviously you put the negative, it's going to change that value to positive very quickly. And what's going to happen is we're going to be centered at 0, 0, and then we're going to go down, or open down, I should say, with that absolute value. Alright, and last but not least, the general form for the equation, y is equal to parentheses, and then I'm just going to go ahead and put the following, which in this case is a, so the a value on the outside, absolute value bar, x minus h, and then plus k on the outside. Alright, so we got 3 of them done. Again, we're going to go ahead and stop here. Again, you obviously have the toolkit page as well, if I want to make sure you have time to finish that. Otherwise, please let me know if you have any questions. Again, the best part about this is we're actually going to be able to graph all of these functions with transformations without even using our calculator, which I think is, again, kind of unique. Most of us, again, will be just fine. Just make sure that, again, if you're having trouble looking at any of these, you make sure you come talk to me. So with that in mind, have a great rest of your day, and we will see you all very soon.